Let's solve LeetCode number 217 contains duplicate. This is a really good problem just to understand sets and just a little bit of sorting and understanding how we can use sets to increase the speed of certain algorithms. Now, as we can see in the problem, we're given three examples. Let's go ahead and try to understand what are the parameters of the problem. Now, we're given an input, which is nums, and we're given an output that we're expecting, which is a Boolean variable. So it could be a true or a false. Now, let's start off with example one. And so our input is nums, and we're trying to figure out if there's a duplicate. And straight off the bat, we can see there is a duplicate here. Now, we need to break that down in terms of programming. So I'm going to zoom in and talk about how we can analyze this problem. Now, we could start with a brute force approach by looking at every possible combination. So I'm going to write that down. Every possible combination of two variables. So what do I mean by that? So this brute force approach of observing every possible combination of two variables is we basically used 2 pointers, and not the programming sense of pointers, but we grab 2 elements, 2 pointers, and look at them. So let's go ahead and try and do that. So let's do 1 and then 2. So this is element 1 and this is element 2. And we're observing if element 1 and element 2 are equal. And we check that it's not. So we're going to move element 2 here and then check. Nope. Element 2 moves here. And then we figured out that there are 2 variables that are equal to each other, meaning there's a duplicate inside of this nums list. Now, this is very inefficient because we're checking every combination of 2 variables without using memory, and that's a lot of overlapping combinations. Let's say we had a list that only contained 2, 3, and 1, right? So if we had a list which only had 2, 3, and 1, we would start off by looking at 2 and 3, and then looking at 2 and 1, and then moving element 1 over to the next element, and then checking. And that's very inefficient. That's O n squared. So this brute force approach is not optimal. Let's talk about the other approach, which is sorting. So sorting approach. Now, if we sort this, we will get 1, 1, 2, 3 in ascending order. It doesn't really matter if you want to descend or ascend, but by default, a lot of languages sorts it from least to greatest. So I'm just going to do least to greatest. And if you notice, when we sort a list of numbers, there's a possibility that the neighboring element, when you're iterating through the list, is a duplicate. What I mean by that is, let's look at element 1 and element 2. Great, we already got a duplicate right then and there. And we would just keep checking if that wasn't true, like this. So we just check the neighbors, and if there's a neighboring duplicate, we return true, else we return false. So that's very simple. Now let's think of this in terms of how you and I would try to solve this as fast as possible. So we would read the list of numbers and then try to recall in our memory, hey, did we see this before? If so, then we did see a duplicate. Now, the way we can translate this into programming is using sets. So I'm going to call this the set approach. There's a tons of other ways to store memory into different data structures. However, sets are the most optimal here. Now, let's say we're looking at element 1, and there's nothing to compare it, so we're gonna put this element into a set, and then let's look at the next the next number in the list. So it's 2. Let's put that down. Let's try to recall. Let's look in the set. That's what we're doing in programming. If we had the number 2 before, we didn't. So let's continue. We put 3. So we're remembering, we're putting these numbers into memory and checking if we've seen it before. And the number 3 was not seen before. So let's iterate and then check 1. Oh, would you look at that? We found 1 in our memory, and we will return true if that was the case. Now, this is the same for the other test cases. I'm not really going to go over. It's a very straightforward approach. And I want to talk about the set approach time complexity. So this set approach is in big O of n notation because we only iterated through the nums list once. We only looked through it once. And then the memory is also O of n. N represents nums size. And that should conclude all the approaches that we can really think of right off the bat. Now, when it comes to programming, we need to weigh our cons and pros of certain approaches. This set approach is the fastest in terms of time complexity. I'm not sure. I don't think I said how fast the sorting approach was, but when we sort things out in most programming languages, it takes a time complexity of O of n log n. And the approach I talked about earlier only used O of 1 because we weren't putting numbers into a data structure to recall. And as we can see, although the set approach is a lot faster, well, not a lot faster, but a bit faster than the sorting approach uses constant memory, which is more efficient. If, let's say, we have a little bit of memory on our program, on our hardware to allocate to, maybe the sorting approach is better. Now, let's talk about the sorting approach. What the sorting approach basically is check neighbor. We're checking the neighbor, see if it's a duplicate. We're going to see that in a bit. So in Python, it's nums.sort, just to sort it from least to greatest, and that's of O of n log n. Then I'm going to use an index so we can look at the neighboring element. And we can represent the neighboring element by just adding a 1. And if we can't find a neighboring element that is the same, then we return false. We didn't find a duplicate. That's what we're saying. Now, this is an n log n plus O of n. However, that gets reduced down to n log n. That's the significant time complexity we get. And this memory is O of 1. And I'm just going to save this for later use, so we could view the comparisons between the sorting approach and the set approach. Oh, and I think I forgot to run it, actually. So I think we got an error. Yes. So our index was out of range. The error could be fixed by just subtracting 1 from the length of nums, because we're checking 2 at a time. So on the last iteration, index 1 would be at length of nums. So that's why we subtract -1 here. So just remember, we're checking 2 at a time. So this can be within range, we're subtracting 1. And that gets our result. So now I'm going to save this for later. Now let's talk about the set approach. So we're basically storing memory and seeing if we recall if we've seen the duplicate before. Now this will take up some memory space, and we'll see how much in a bit. So we're going to start by creating a num set. This is how we can initialize the set. It's basically an unordered set of numbers or items where we can instantly check if we placed a certain item in the set an O of 1 time. So it's really quick. We don't have to iterate through an array or anything. It's just check the item real quick. And this is where we're going to allocate our numbers that we've previously seen before inside this data structure. So let's iterate through the nums list. And if we previously seen it, so if it previously mapped, we're gonna say that it was a duplicate and return true. So if num set, if num in num set, that means it was previously mapped, we're gonna return true. And the reason why we started with that is because we want to check instantly on the iteration we're at the element we're at, and check the previous set. This order really matters because then we're gonna map out the previous number down here. So map previous number here. And we're gonna return false if we didn't see a duplicate in our memory, in our set specifically. We could also call this previous set. Up to you what you really want to call it. I'm calling it num set because in worst case scenario, we're gonna map out or set every number in here in O of n. And since we're only iterating through it once, it's O of n as well in time complexity. So the memory complexity is O n and the time complexity is O of n. And that's how we could solve it in Python. So here you want to try to analyze what are the benefits and the cons of going through the set approach and the sorting approach. If you're in an interview, I highly encourage you to talk about the differences between these approaches and which one would be more optimal for certain scenarios. Now we're gonna run the code, see if it works. It worked. I just ran it, passed all our test cases. Great. So just to show the set approach, we're gonna go ahead and submit our solution to LeetCode. And we see passed, and we see our runtime and our memory. This won't always be accurate, but it gives you a rough understanding of where you're at. Sometimes this can range between, for me, 90% to 60%. Really varies. Now let's talk about how to solve this in C++. Specifically, LeetCode number 217 contains duplicate problem. Now, we need to start off with using namespace std, just because LeetCode has this already built in. Remember, this is not good coding practice, but for now, for data structures and algorithms, problem solving, we're going to use this namespace std. And we need to create our class solution that contains our method to solve this problem. Now we're outputting a boolean, and our input is a vector, which is nums. And right off the bat, we need to include a certain library. You don't have to do this in LeetCode. However, it's good to understand where these algorithms, these data structures come from, what libraries exactly. So it comes from vector. Now I'm going to start off with the sorting approach, since we saw that the brute force approach is not really needed, and we'll do it in the C solution later, just because it's like it's the exact same answer in C programming language for C++. So we need a sort, and this is how we can sort the numbers vector. However, sorting function comes from the algorithm library. Then we're going to iterate through the numbers vector and check each neighbor. And we're going to use an index so we can check the neighbor. So this is how we can check the neighbor. So it's very similar to Python. So we just add 1 to the current index. So we're essentially checking 2 out of a time. And returning true if we find a duplicate. If we cannot find a duplicate, we are returning false. And as I mentioned earlier, it's n log n. Our sorting and our memory, nothing was stored, it's constant space. Our memory is of 1. Now I'm gonna go ahead and save this for later. My bad. We should first create the test cases and check if this works in the first place. Now we need to include this library to assert check every test case. We need to initialize our examples up here. And let's do it for the rest of the examples, like so. And I'm going to create my own test case just to check an edge case where our vector is the size of just 1. Now, when we try to solve these problems, we should always try to think of these edge cases, try to solve them, because the program might not work in every case. So we create our own test cases. Now let's run it. And we see we had an issue. I'm a little too used to using Python. However, we could just delete the semicolon. Technically, we can do this. However, this is a one-liner if statement, so we can also leave it like this and have a cleaner look. So I'm going to run it. And I have another issue where I forgot a semicolon for our class. And now we got it. After 2 failed attempts, we got it. So remember, semicolon after we close our class, and don't use colons. It's not Python. Now we're gonna try to move on. We're gonna move on to the set approach. Now let's begin the set approach. So right off the bat, we need to include a library. So we need to include the unordered set. So we can have the data structure of the unordered set. We're going to call it num set. This is where we're going to put every previously mapped, we're going to map every previous number into num set to check if we can recall if we've seen the number previously and of 1 time. So it's a really quick way to check your data structure for a certain item. Now we're going to iterate through the numbers vector. Then we're going to check if num was previously mapped to set. So this is a one-liner if statement where we could just put return true here. We don't have to have the curly braces, and we're gonna map the number that's about to become a previous number into our set. And if we're able to iterate through the entire thing without being able to find a duplicate, we're returning false. Now, we only iterate through the nums vector once, so that's of n time. And we're mapping every number into a set, which is num set. That's of n time in worst case scenario if it goes through the entire vector. And that's how we can solve it in C++. So we're going to try to go ahead and run it. And we were able to run it. And I'll go ahead and try to run it on LeetCode. So here we're on LeetCode. We're going to run the test cases. See that everything worked out. I'm going to remove this actually real quick and remove this too. And let's submit the solution, see what we get. As we see, we get pretty close. Everyone has about the same solution.
Yeah, it's very, oh, this is a sorted approach. It could be off. Let me go ahead and try to run it one more time, see if we can get a faster time. For some reason, it always varies. They should really improve this. As we see, we get 72. Let's solve LeetCode 217 contains duplicate. Now, when we're trying to solve this in C programming language, we need to remember that a lot of data structures aren't included in the C standard library, such as sets and hash maps. We just have to include a lot of these things in. So let's look at the first input and try to see how we can solve it. So we have nums as our list, and we're trying to figure out if there's a duplicate. So the first way we're going to try to solve it is through the sorting approach. So I'm going to talk to you about my process of trying to solve this. So when we sort this, we get 1, 1, 2, 3. And what I'm going to try to do is check in sets of 2 if there's a duplicate. So like that, and then like that. So let's define our function. Now our input is nums, and keep in mind, uh, arrays work a lot differently in functions in C programming language versus like C++ or Python or other languages. We always need to carry in the size of the array, or we use a library to try to solve that problem out. But in most cases, we have the size of the array as an input. So right off the bat, we're going to use quick sort to sort from descending to ascending order. And in C programming language, qsort is built in where we have a couple inputs we can put in, which is the array, the size of the array, and the size of the type that we're working with. So it's the size of each element in terms of types. And then we need to use a comparison function we need to create to use qsort. So every time we use qsort in this fashion, we need to make a comparison function. So because we have an array of nums that are represented in integers, we're going to return an int. And our first input is going to be a constant A element and a constant B element. And we're doing from descending to ascending order. We're going to return least to greatest. Now that completes our qsort, and it sorts that in a time complexity of n log n so far, so keep that in mind. And now we're going to iterate through our sorted array and check pairs of 2 at a time, neighboring elements. Now we need to iterate using an index, because in C programming language we cannot iterate per element like in other C++ programs. So we check pair or check neighbor if they are duplicates. So num's index represents the current index or the current element we're looking at, and index plus 1 is the neighbor, and we're going to return true if it's a duplicate. If we're able to iterate through the entire array, we're going to return false, and that's how we get our solution. Now let's analyze the time and space complexity of this. So we iterated through it in ov(n) here, but our qsort is n log n, which is larger than n. So simplified is O of n log n in terms of time complexity, and O of 1 constant memory complexity, because we didn't store any numbers into a data structure. Now let's try to go ahead and try to see if this is correct by using test cases. I also forgot to include a certain library. Boolean isn't always included. I mean, the the Boolean type isn't included in the C programming language, so we need to include it up here. And since we're going to use assert functions, we need to include that as well. So let's create our examples now. Just a note, in C programming language, we can grab the size of array by grabbing the entire size of the array times the type and then divided by the type. So this is how it looks like. So this is how we can get the actual size of the array. And this is how we're going to create our test cases. Okay, I have typed out every example test case we're given. However, we want to check for an edge case where size of array is just the size of 1. So this is test case 4. So this is the size 1 again. And we're going to create the test case. And let's run our sorting approach. And I forgot to include that this comes from a certain library, qsort, and it comes from here, stdlib.h. stdlib.h. Let's run it one more time. We finished. So it passed all the test cases we checked here. Now, in terms of what this is good for is saving memory. However, it's a little bit slower on the next approach we're going to look at. We're going to try to reduce this down to O of n time using a set approach. However, if you're trying to solve something where you care about memory space, maybe this approach is better. So let's try to solve it using the set approach. Now, right off the bat, we need to include a certain library that is not part of the standard C library. So I'm able to just include it and use certain functions. However, keep in mind you might need to download this online to find this out. But I've already included it into my C programming language header files. So now what this allows us to do is use hash map functions. However, we still need to create our set data structure. So the reason why we're using a set data structure is to look up values in O of 1 time. Reason being is because we're going to iterate through the numbers array, then try to recall, or we're going to recall any numbers we've noted down and see if it's a duplicate. And a set data structure is perfect for this. So we're going to use typedef struct. So we can use multiple instances of this if you want to. And we're only going to use a key item of a hash map. This is practically a hash map. This is a set specifically where we only use the key values. And we're also going to use something called a hash handle that's included in the uthash.h header file. So this makes this structure hashable. We're going to call this a set. So now we created a set data structure. We're going to initialize our set in our problem, and we're going to call it num set. So we're mapping out every number in the nums array, and this is how we can initialize it. Now we can go ahead and iterate through the array. So we're going to use an index value to iterate through the array. Now, right off the bat, we're going to search for num set if current number has been mapped previously to set. So we can use a built-in function called hash find int. We're basically finding an int value in num set, and we're gonna look up the current element, which can be represented as nums idx. And if the element is found, we're gonna break out the loop. Now here normally I would return true or false. However, um, I'm running this locally and I want to free up memory space every time I use this data structure at the end. And for that to happen, I need the program to always reach this area right here where we free up the hash set. Now, because of that, we need a flag, which we can represent it as Boolean flag is equal to false. This is where we initialize it, and we can change the Boolean flag up here to true. And because of that, after we free, I didn't notice I typed that wrong. Free up the hash set. Sorry. I could return it down here at the end. After that, we want to map previous nums into nums set. The way we can do that is by first allocating memory space for the data structure, specifically each element. And we're going to use pointers to store these keys inside of this basically hash map, but it's a set. So we point our nums element to our key, and then we add it using a hash add int function built into our library. And this is so far so good. However, now we need to free up the hash set. And we could do it by iterating through the hash set using this function hash iter, using the hash handle, the specific set, and all the items inside. Imagine this as a for loop iterating through the hash set. And we use the hash delete function where we delete the current element that's being looked at in the num set, and then use free element. And this should work. Let me go ahead and check everything real quick. So we initialize, we set a flag. The flag only changes if we found the number inside num set. So far so good. We free up the hash set, and so far so good. So I'm gonna run it now. See, hope it works. Great, it worked. Now I want to discuss why I'm doing this in C programming language over C++. I'm only going to do easy problems in C programming language, specifically because I have some experience in embedded systems and I want to see how these algorithms can be coded up in C programming language, language I use a lot for embedded systems. It's just practice for me, and it could give you a better understanding of how these data structures are created from scratch and used. Now I'm going to try to run this in the LeetCode websites just to show you how it works. By the way, I forgot to mention this is ov_n log n. ov_n, sorry. And the memory complexity is ov_n since we stored every number inside of the num set, and n is represented as nums. I also want to talk about how in LeetCode, there's certain problems that we don't have to free up the hash set. It kind of does it by itself. So I'm going to modify this. So if I run this, we can see it will work. Hoping it works. Yep. So it will work. However, if I want to make it a little bit faster just for the website, I'm going to remove this and remove the flags and rewrite this a bit. So it could be just a slightly bit faster. This is a little bit more easy to understand at the same time. We don't have to worry about freeing memory space after the use of a data structure. So when I run the test cases, it should work great. And let's submit it, and it worked. I've ran it a couple times before just to show you that in certain cases, it could run a lot faster. You know, this isn't entirely accurate. However, we can see there's a big difference between here to over here. So as long as we're within this range, we're fine. And we understand a big O notation for time complexity and memory complexity. As we see, we use a lot of memory space here, so we're not doing that great in that department. However, if we use a sorting approach, it'd be a lot better. We'd probably be around here. And that concludes programming this problem in C. So let's solve this problem in Java. This problem contains duplicate from LeetCode. number 217. Now we're given an input of nums, and we're trying to figure out if there's a duplicate inside of the array of nums, or a vector, or list, whatever you want to call it. And as we could see in the first example, 1 and 1, that's true. It's a duplicate. Example 2, 1, 2, 3, 4, there's no duplicate, false. And then there's quite a bit of duplicates here, right over here in example 3. There's multiple duplicates, so it's true. So first off, I'm going to go ahead and do the sorting approach. So what this does is we sort it. So when we sort an array, it comes out looking like this: 1, 1, 1, 2, 3 for example 1. And we're going to check in sets of 2, just like this: 1, 1, 1, 2, and 2, 3. However, in the first iteration, right away, we see 1, 1 is a duplicate, so we return true. So pretty straightforward. We need to include certain libraries. We need to import certain libraries, specifically the arrays utilities. And now we're able to sort our nums array. And now we're going to iterate using an index and check 2 numbers at a time. And I'm going to actually subtract -1 right here since we're doing 2 at a time. And this is how we can check neighbors. By grabbing the current index and adding a 1, check if neighbor is a duplicate. And we can return true right down here and return false if we didn't find a duplicate throughout the entire iteration. So I wrote some test cases down here. This is example 1, 2, and 3. However, I want to create another test case where it's example 4. I want to have a edge case where we check an array of size 1. So I'm going to run this, and got an issue. I wrote this test case wrong, so let me go ahead and fix that. It should be on the outside, the false. So let's run it one more time and see that we failed to include int here. Let's run it one more time, and we got it this time around, finally. So pass all the test cases, and the sorting is an n log n, and then we're also adding an n because of this for loop. However, we can simplify this down to just n log n, since that's a larger computational time than n. Also, our memory complexity is going to be O of 1. We didn't store anything into a data structure, so it's O of 1. It's constant memory space. So I'm going to comment this out and try doing a different approach where we use a set. So right off the bat, we're using hash maps and hash sets. So we need to import that. And so we're going to iterate through, let's use example 1, the array. And I'm going to go over 1 and then say we're going to have a nums map where we store what we've seen so far. Actually, let's call this num set specifically. So we went over 1, so we can map out 1. We went over 2 now, and then we went over 3 just now. And now we're at element 1 again. So we're going to check num set and see if 1 was previously mapped specifically. And if it was, we return true. That's a duplicate. So that's how it's going to work. That's how our num set works. And we can instantly look up these values in O of 1 time since we're using a num set. So let's initialize our set with nothing. And then we're going to iterate through each number in nums. Then check if current num was previously mapped. We can do that with this if statement right here. And we will return true. Else map current num. And we can do this by adding the current number to our num set using the add function. And then if we iterate through the entire array, we're going to return false if we didn't find a duplicate. So let's check if this logic works. So we initialize the set, we iterate, check if current number was previously mapped, return true. This order matters, by the way. We need to have this if statement first before we map anything. else map current number. Yep, seems about right. So I'm gonna run this, and it worked. Now let's talk about the time complexity. So it's oven and oven since we only iterated through it once in linear time, and we mapped every single number in worst case scenario to num set. So that's how we can solve it in Java. So you gotta weigh the options of better memory complexity or better time complexity according to your problem. However, these approaches are pretty good. I would personally go with time. I like faster time, but it really depends on the problem. So that's it. So now let's run our code on LeetCode. See if it worked. I'm gonna delete a couple comments and pass our test cases. So let's submit our solution. Great, it worked, and it's pretty fast and doesn't take up too much memory space. So that concludes our Java solution.